IP addressing. In this nugget, we discuss IP addressing, and normally we look at an IP address and it might be 10.8.7.56 or something like this, and it looks pretty self-explanatory to us that it's just a series of numbers. But beneath all of this, there are actually numbers that you need to understand that are binary numbers, whereas these are decimal numbers. They're actually binary numbers that you need to understand, and we'll take a look at that because you have to know the binary in order to make sense of anything in terms of IP addressing. We'll also take a look at a subnet masks, and this might look something like 255, .0.0.0 or something like this. And the subnet mask is what's going to be used in conjunction with the ANDing process to allow a host to determine whether or not a destination computer is on its local network or on a remote network, and whether it needs to send packets through a router. Well, let's take a look at address classes. There's A, B, and C, which we'll primarily be dealing with. There's also D and E, but they're outside of our current scope. And then there's private IP addresses, and this will help to make sure that you can use pretty much an arbitrary range of addresses for your own purposes without actually having to buy or lease any addresses. Now, first, before we get too involved in this, I want to point out that if you're already Cisco certified, your CCNA, CCDA, CCNP, any of the Cisco certifications, we're already very familiar with IP addressing, or even if you're not Cisco certified, but you've already been through the whole rigmarole with IP addressing and you understand the whole thing, and you understand all the binary numbering and all of that, then let me encourage you, you could probably go ahead and skip this particular nugget. If you're also very familiar with custom subnet masks, then you could probably skip the next nugget as well. For the rest of us that haven't learned this yet, or like me sometimes, for those of us that might need a refresher from time to time, you might want to go ahead and take a look at these two nuggets just to make sure that your mind is in gear for the IP addressing schemes that we'll be looking at. Now, also, some of the stuff that we'll be looking at, I kind of liken to parallel parking. See, here I live in Phoenix, and since we're not really in a densely populated area, we're out in the suburbs and all that kind of stuff, and since there are several mountains throughout the city which spread out the city, we don't have dense areas like you might have in some other cities, like Hong Kong or London or New York, where you've really got to fight for parking spaces, and if you can find one, chances are you're going to have to parallel park. Well, I can't remember the last time I parallel parked. However, any qualified driver should know the basics of parallel parking and how to do parallel parking. Same thing with our subnetting ideas here, our networking, our IP addressing, all that kind of stuff. You probably won't have to use that every day as an administrator with Windows Server 2003, but you should be familiar with it so that if you ever do have to work with it, it's not totally foreign to you. Well, you're probably pretty familiar with what an IP address is if you've been in computing for very long and if you've been on the internet for very long, because every system on a computer network has to have a unique IP address. And in fact, here I've got in this Word document an example of just one IP address, and this just happens to be a Class B address, which we'll be talking about a little bit later on. Now, as we see this IP address, just take a look at it, and then think to yourself and answer to yourself, how many numbers are in this IP address? Okay, and I'll just play the Jeopardy music in the background here. Dum 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 dum. Okay, you got an answer for me? Well, if you said there are 4 numbers in an IP address, you're wrong. I'm sorry. It was kind of a trick question, though. Because you see, us humans, we look at this and we say, okay, I got one number here, that's 172. Then there's a second number, 16. Then there's a third number, 48. Then there's a fourth number, 221. But you see, we only see this number as a concession to us weak-minded humans, because your computer actually sees a different number than this. Because you see, what your computer actually sees is this single number, and that answers the question of how many numbers are in an IP address. It's really just this single number or string of zeros and ones, and there's 32 of them. And this is what we call binary numbering. But as a concession to us humans, we are able to see decimal numbering just so that it makes it easier to read and so you don't go blind trying to decipher all these zeros and ones down here. So unless you're one of the stars of the Matrix that can just look at characters drifting down out of a green screen and suddenly somehow interpret that as a woman in a red dress, then you'll have to be able to use decimal numbering when we just look at IP addresses in casual administration. But in order to understand things like IP addressing and custom subnetting and default subnets and all of these other kinds of things and network IDs, you're going to have to really understand that it's all actually this series of zeros and ones in binary numbering. Now, there are a couple things we can do this to make this easier. The first one, of course, is just the decimal conversion. And the second thing is you can even split up this binary sequence of 32 numbers or bits by separating it into octets. And if any of you are students of language of Latin language or of any other language that has Latin roots, then you know that octet has to do with the number 8. So we can count over 8 numbers, 1, 2, 3, 4, 5, 6, 7, 8, and we put in a dot or a period there. And then we separate all of these out until finally, after we put in all the dots there, we're able to make a little bit more sense of this binary numbering scheme. Now, don't get too intimidated, by the way, as we look at this. If you think, oh, for crying out loud, James, you tell me I got to be able to figure out what all these zeros and ones and all that kind of stuff are? No, because you get to cheat. And you get to cheat almost anywhere you are. There's a number of ways you can cheat. And believe me, I'm the master at cheating here. What we can do is to either use the Microsoft calculator, or you can use some subnet calculator that you can download for free off of the internet. But because we're trying to show you here the basics of how to decipher all this and interpret and translate all these numbers, we're just going to use, at the most, the Microsoft calculator. So, one way that we could do that then is if I look at this 221 and I just copy that using Control-C on my keyboard, and I go up here into the calculator, which is in the scientific view, and I also use digit grouping to make things a little bit easier. Then I'll just paste that in, the number 221, or I could have typed it in, but I'm just too lazy to do that. Now we can convert to binary by clicking on BIN on your on this button over here, and I also like to use keyboard equivalent, so I just hit F8, and we now see the equivalent in binary, and that is 1101, 1101. Here we go, 1101, 1101. That's 221. And of course, the calculator is your friend. In fact, the calculator is always right, provided you enter the data incorrectly. So let's just say this right out from the beginning. Always trust the calculator. In fact, let's make that our mantra for this particular nugget. Let's all say it together. Ready? Trust the calculator. Say it again. Trust the calculator. Okay, I hear you all saying it. Trust the calculator. You're doing great. Keep going while I move on here. Okay, now what we got here is this calculator equivalent of a binary number, but how do we understand what that is? It's still not really at a point of where I understand why all of this means the number 221. Let's take a look at what that actually is. You see, as we look into this, then we have to understand that each one of these bit positions, this bit position here, this first bit position here, and this bit position here, and this bit position here, you see, all of those actually represent a number. Don't think that 1 is actually a number there by itself, really, that we count up. It doesn't mean 1 plus 1 is 2, plus another 1 is 3, plus another 1 is 4. No, don't think of it that way. All these bits mean, and this is true of most binary systems, actually any binary system, is that the 1 simply means it's on or it's counted. The 0 means you ignore it or it's not counted. And each one of these bit positions is equivalent to a decimal number that we can see down here. So let's start at the far right. We go with a 1 here, and then what you do in order to go through this is you just double each number. 1 doubled is 2, 2 doubled is 4, 4 doubled is 8, 8 doubled is 16, 16 doubled is 32, 32 doubled is 64, and 64 doubled is 128. So then let's go ahead and take a look at each one of these binary bit positions, and if it's enabled or turned on with the number 1, we'll count that number in. So if we see that the first position on the far left here, a 1 means it's on, that means I'm going to count 128. So I'm going to type that in here, and we'll just add these all up together. If I can type right, there we go, 128. Then we'll add any other numbers that are also turned on with the 1-bit position. My 64 is turned on, so I'm going to put that in. My 32, as you can see here, is not turned on because there's a 0 in that bit position, so I'm just going to go ahead and leave that at 0. Now, I can also just ignore it, but I'll type it in so that we have some representative for each bit position here. Then for the 16, there's a 1 there in that bit position, the 4th position over, so I'll type that in. I'll add that up. And then I've got also my 8 plus my 4, and then my 2 bit position here. My 2 in the decimal is not turned on in the binary bit position. So I'm going to again go to a 0 here, 0, and then we'll add in a number 1 for the final bit position. Add that all up, equals 221. You don't believe me? Use the calculator. Remember the mantra? Always trust the calculator. Just add them all up and you'll see that. And then to cement that even a little bit further, I've gone ahead and put the binary bit positions underneath each decimal number here just so you can further cement that and make the correlation a little bit more clearly here. Now, one thing I didn't discuss, however, was a subnet mask. A subnet mask helps the local system that is communicating on the network to identify whether packets that it's trying to send out should go to another host on its own network or to a host on a different network. And there are different ways of describing the term network here as well in terms of IP addressing. And you'll just hear them described different ways in networking parlance. It could be called a physical segment, or a network, or an other network, or a remote network, or any of those kinds of things. But basically the idea here is, at least from a fundamental level, is that we look at a router, which I've got here in the middle, and a router will divide these two networks, so that we have a router dividing this network from this network. Now, why might I want to do that? Well, I just only have two pictures of two servers on each one of these networks. However, let's just assume that on each one of these networks we've got 800 hosts. So 800 hosts over there, 800 hosts over there, including my desktop servers, printers, all that kind of stuff. Well, see, without this router in the middle here, and if I just connected all of those onto the same network, that would give me 1,600 hosts on the same network. Well, that presents a few problems. First of all, it's going to be a very busy network. Even if it was 3 a.m., nobody's in the office, nobody's using any of the servers, even at rest, that network's going to be pretty busy with things such as keep alive packets and all other kinds of traffic that still goes on. And then you add daily work tasks to that during business hours, and that gets to be just swamped with way too much traffic on an Ethernet network. And that's generally what I'm going to be considering that we're using unless I specify otherwise. You see, an Ethernet network is typically limited to 1,024 hosts on any given network. Now, we're not going to consider things such as switches in this discussion, and a switch will help to break up that collision domain. So, practically speaking, I could substitute a router here for a switch, which would still divide the two networks. But we're going to be talking about networking in a more basic format here. We'll generally be just discussing things such as routers. Well, this server here will identify whether or not a packet that it's sending out should belong on its own local broadcast domain and just allow it to be broadcast here, or whether it belongs to a remote network like this one over here. If it's destined for another network like this remote one over here, what happens is it will send that packet, instead of broadcasting it, send it to the default gateway IP address, which is the interface to my router. Then the router has knowledge or a routing table of other networks that it can then send that packet to. So if that router knows about this network over here, then it will say, oh, I know who you're looking for. You're looking for someone on this network. It'll send it out of this port and allow it to broadcast here. And the way this original host knows whether or not to send it to its own broadcast domain or to send it to this interface on the router, the default gateway, is by using something called the ANDing process with this subnet mask. Now, the ANDing process takes the IP address from the local host here, and it sends it to its binary equivalent, which we see right here. That's the binary for 192.168.1.2. Then it uses the subnet mask as kind of a filter, if you will, to perform the ANDing process. And by the way, in case it sounds strange, it's ANDing, not Andy, but ANDing. And it takes that subnet mask, and it does what we've done in grade school or elementary school, where you take a 1 and a 1, and you know that the equivalent of those two bits, if they're both turned on, is a 1. And we take a 1 and a 1 here, and that equivalent is a 1. Here we have a 0 and a 1, that's a 0. Anyway, it does that all the way down the line here. And the result of the ANDing process at the end of the subnet mask, right at this point, is what we see over here. Okay, so that's the result of our ANDing process. Now, if this host is trying to communicate with a destination that is 192.168.1.209, then it also does an ANDing process on that destination host, and it does so, and it comes up with the same conclusion by the time it's done ANDing. And so we see that all of these numbers, if you want to look at them all individually, all of these binary bit positions are all exactly the same between these two hosts. Now, if it turns out that they are both the same, like we see here, that means it will send it to its own broadcast network. Now then, how will this host know that it's supposed to send a packet to the default gateway instead of allowing it to go around in its own broadcast domain? Well, it starts off doing the same thing. It still does ANDing, and it still has within its memory, actually, this ANDing result for its own IP address, and then it compares it to the destination IP address. And in this case, if it wants to send something to 192.168.2.2, when it does the ANDing process, notice that here we have a different result. It's mostly the same all the way through here, but the last two bits, notice how they're different? Well, since they're different from its own ending result, it says, hey, you're not on my network, you're on somebody else's network. So I'm going to send you, since you're on a different network, to my default gateway's IP address, and then the default gateway or the router will be responsible for forwarding the packet on. Well, that diagram that I showed you and the ANDing process and all that kind of begs another question, and that is, how do I know what IP addresses to use for my network? How do I know what subnet mask to use for my network? Well, years ago, an organization called Internic, and specifically a guy that used to work there, he's passed away since then, but his name was John Postel, and he was responsible mostly for distributing ranges of IP addresses. And that's back when we had about 4 billion addresses, and they were given out pretty freely. But then the Internet came along, and so that kind of got tightened down pretty quick, and now there's not really any addresses you can get from Internic any longer. Instead, you'll probably get them from an ISP or something like that. And when you get your address, you're going to get one of 3 classes for common network communications. Now, the addresses that are available are Class A, B, or C types of address classes. We'll be discussing those shortly. There's also a Class D, which is used for multicasting and not part of our discussion, as well as a Class E for experimental purposes, also not part of our discussion. Now, for normal network traffic, it's going to be a Class A, B, or C address, and with this, we will have, for example, with Class A, a specific network ID. The network ID identifies which range of addresses are available to that specific class. So, for example, with Class A, I could use any IP address for a Class A address that started with a 1 dot and then any number. So it could be 1.2.3.4. That would be a Class A IP address. And then I could go all the way up to 126 dot any number there also for Class A type IP addresses. Now, one thing that you can identify by looking at a Class A address is that it always starts in binary with a 0. So let's go ahead and take a look at a Class A address just real quick here so we can get a good example. If I had a 1.5.6.7 IP address, then if we looked at that in binary, then we would see the first octet would be 1, 2, 3, 4, 5, 6, 7. 8th bit would be turned on. That's our 1-bit position, remember. And then we would have our .5, .6, .7, and so forth at the end. But the key there is any Class A address always starts with a 0. And that's why I've got this in parentheses out here. The binary first bits always starts with a 0. Okay, now let's also take a look at the default subnet mask. That's always going to be a 255 in a Class A network address. Now, when we later on talk about custom subnet masking, some of these numbers might change. So these might change, but at least that first octet's always going to be a 255. So if we put that in binary, a 255 means that all of the bit positions in the octet are turned on. So that would be 8 ones, 1, 2, 3, 4, 5, 6, 7, 8, which would be the equivalent, of course, then, of 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. Wow, that was a mouthful. Okay, so we added all those up together, equals 255. And then I could put 8 zeros for each one of the remaining octets, but I'll just shorthand it and put 0.0.0 here. And of course, 16 billion hosts is an absurd number for a single network, but that's where custom subnetting comes in a little bit later on. Now, first let's go back now to a Class B address. That can be any decimal number that starts between 128 up through 191 in the first octet, and then dot whatever for the remaining octets. The first 2 bit positions in a Class B address will be a 1 and then a 0. And then the default subnet mask is 255.255, 16,000 networks, 65,000 hosts. Class C starts with anywhere between 192 in the first octet up through 223 in the first octet, dot whatever, and then the first 3 bits there will always be a 110 in a Class C network. The default subnet mask for Class C is all 255.0, and you can have up to 2 million networks and then 254 hosts per network. Now, notice the correlation here. The more bit positions we reserve for the network side, and these subnet masks where it has 255 are all reserved for the subnet portion or the network portion. So we have a network portion on a Class A address of the leftmost octet. So there's 8-bit positions reserved for the networks, and there's 8 plus 8 plus 8, there's 24 bit positions reserved for hosts. Now, there's a correlation here. The more bit positions you have reserved for hosts, of course, the larger your number for hosts is. The more bit positions you have for the network, 255 in this case, then the more network numbers you can have. So when we get down to Class C here, for example, notice that our number of networks has increased, but because now we only have 1 octet left for the hosts, that is decreased to 254. Now let me also go over here and look at this 126 in the network ID, the final network ID, for Class A addresses, and then where we pick up at 128 on Class B, looks kind of like we're missing something between the two. 126, shouldn't there be a 127 somewhere? Yes, there should, and there actually is. It's a Class A address, but it's known as our loopback address, and it's any IP address in this entire Class A range. So, the purpose of the loopback address is to verify that our TCP/IP stack that's loaded, our software stack, is loaded properly. It does not diagnose hardware problems with the network card. So if I go to a command prompt and type ping 127.0.0.1, it'll give me replies because it's sending a packet down and up through my TCP/IP stack, getting a reply back. This verifies that my stack is okay, but I could still have a defective network card, and this would not diagnose that because it does not actually touch the hardware. Now, notice that I can also ping 127, if I can type 127.255.255.254, and still get a reply back. What does that mean? Well, that means that I can use any combination of bits or numbers throughout this whole address range, which gives me a total of, since it's Class A, 16 million different ways of pinging myself. That sounded kind of dirty, but that's not how I meant it. You get the idea. There's a whole Class A address range just for the loopback address. And like I said, it is very useful for diagnosing the IP stack. And that's also an indicator that when they first divided up network address ranges at Internet, they never had any plans that the Internet would become so big and this would become such a giant waste of addresses. Anyway, that's okay because we are out of addresses that are publicly assignable. You can't get them anymore. But in your own internal networks, you probably won't need that many, if any at all, because you only need a public IP address that's what most of these addresses are, public addresses that are available and routable on the Internet. You only need that for your Internet-facing routers and any other network connections that you have to the Internet or to the public Internet. And you can't just arbitrarily pick a number out of the air. You can't say, hey, for our router that faces the Internet, let's give it an IP address of 191.5.6.7. Well, there's a chance that somebody else is already using that IP address out there on the Internet and can cause some network problems out on the Internet. So you have to go through, typically, your ISP to get an assignment for a public IP address that way. But for your internal hosts, where you'll have most of your hosts in most organizations, that's where you really need your IP addresses. And it might be pretty expensive to buy or to lease a whole broad range if you got, 10,000 desktops, 10,000 hosts that you need for your private network. So, and you don't really need that because you have other network equipment such as routers, proxies, other kinds of things that can handle all the Internet traffic for you, and they're the only ones that might need a public IP address. So instead, in your internal host, you can use what we call private IP addresses, and you have 3 different types that you can use. You can use a Class A IP address, which would be anything in this 10 dot range. You see there it starts with 10.10.0.0.1, that is, a Class B address range, or you can use a Class C address range, and each one of these uses the default subnet mask for its class. And most home networking equipment, like your little Linksys routers that are ubiquitous in just about in every small office in the world nowadays, I think, they typically are default assigned to 192.168.1.0 in that network ID. In a lot of organizations, a lot of corporations, we typically will use something in the 10 dot range. That's because we get such broad flexibility there. I mean, we get 16 million hosts if we want to use that many within our internal networks. And another advantage, by the way, of using a private IP address is these addresses that you see here, Class A, B, and C addresses, are not routable on the Internet. So, if someone out there on the Internet, some evil, nefarious network hacker is trying to direct hack one of my hosts, and it's got an IP address of 10.5.6.7, then they will not be able to attack it by IP address from the Internet, because Internet routers will just drop those packets immediately. And I'll put all this up on nuggetlab.com for you. Addresses.doc is the name of the file, and that way you can just use it for your own reference. Now, this is again a parallel parking idea. You don't have to use it every day, but it's generally considered that you should know this information. So that if someone says, hey, on our network we have a 156.17.8.9 IP address, then you should be able to immediately in your head say, oh, they're using a Class B address range. In this nugget, we discussed IP addressing, and we saw that although we humans have to look at a decimal number in order to be able to read it, the computer actually looks at 32 bits in binary numbering divided into octets, or 4 different pieces of 8, if you will. And you have to understand the binary numbering that we saw in order to understand IP addressing, and especially for our next nugget coming up, which is how to custom subnet. We also took a look at the purpose of the subnet mask and how it works. And this is what's going to help to work with the ANDing process to determine which hosts are local and which hosts are remote in network communication so that it knows whether or not to send packets to a default gateway or a router. Then we look at address classes. Class A, B, and C addresses are what we will use for normal network communications. And then we also took a look at private IP addresses, which are kind of an arbitrary series of numbers that you can use from within a range that you can use for your own networks without having to buy or lease additional addresses. I hope this has been informative for you, and I'd like to thank you for viewing.